In this module, we're going to talk about bond energies. So, at this point, you know that the atoms in a chemical compound are held together by chemical bonds, ionic and covalent are the kinds we've seen. Well, bond energy is defined as the amount of energy it takes to break 1 mole of these bonds. And the thing is that because how much energy it takes to, say, pull an oxygen atom away from a hydrogen atom depends upon its environment. That is, what other molecules are around it, what other things are pulling on them. That what we do is we take an average of the bond energies, and that's what we make a list of. So it looks like this small list of bond energies, average bond energies. And so if you were to measure experimentally the carbon-hydrogen bond energy in some molecule, it might not be 413, but it's probably going to be somewhere close to that. But its exact value is going to depend upon what other atoms are around it, what environment it's in. Let's see. One thing to notice, you're going to refer to this when you're doing some problems, is that because carbon dioxide shows up so much, its bond energy is 799 kilojoules per mole as opposed to the average bond energy of a carbon-oxygen double bond being 745 kilojoules per mole. So watch out for that. If you need these numbers and carbon dioxide's in there, make sure you use this guy and not this one up here. So how can we use these? Well, we can use these to approximate the change in energy for a chemical reaction. And it looks like this. This sigma means the sum, so we're going to add up. This means add up all the bond energies of the reactants and add up all the bond energies of the products and subtract the products from the reactants. The concept here is that even though this is not the way a chemical reaction actually occurs, what we're imagining doing is taking all of the bonds and breaking them apart until we have just atoms, and then sticking the atoms back together, making the products. And so the amount of energy it takes to break all those bonds is the sum of the bond energies of the reactants. And when we put them back together, the amount of energy that's released is the same magnitude but opposite sign of the amount of energy that it took to break them. So let's do an example. This reaction right here, this methane, it ends up reacting with oxygen to make carbon dioxide and water. Now, what you need to know, and you're going to learn you probably already know how to do it, but in the next module, we will talk about Lewis structures. Lewis structures let you know that, for example, in the oxygen molecule, there's a double bond there, not a single bond. Methane, CH4, is just all 4 hydrogen atoms are attached to the carbon with single bonds. You need to know that. Carbon dioxide looks like that, and water looks like that. So we want to approximate the change in energy for this reaction using bond energies. So all we're going to do is imagine taking the 1 methane molecule and the 2 oxygen molecules and break them apart, pulling the atoms away from each other, and then putting them back together as carbon dioxide and water molecules. And so the equation looks like this. There are 4 carbon-hydrogen single bonds. So right here, we took 4 times 413 kilojoules per mole. Now you can think about this 4 as being 4 moles, so the moles cancel. And we're also pulling apart 2 oxygen molecules, and there it's an oxygen-oxygen double bond right here, 495, so 2 times that because there's 2 of these guys. So that's breaking apart the bonds in the reactants. And now we're going to put them back together and make the products. So there's 1 molecule of carbon dioxide. Remember, CO2 is down here, and each carbon-oxygen double bond is 799 kilojoules per mole. Multiply by 2 because there are 2 of those bonds. And we're also going to make water. In each water molecule, there are 2 oxygen-hydrogen single bonds and 2 molecules of water. So there's 4 of those bonds altogether. 4 times 467, which is right here. We put those numbers in, we get negative 820 kilojoules are released when 1 mole of methane reacts with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water, approximately anyway.